Today, it's our pleasure to have Wei Li from Rice University to give a talk on the small system flow. Wei actually is well known in the heavy ion community, and he got his bachelor's degree from University of Science and Technology of China in 2004. He went on to MIT, did the PhD, I think with Gongser, until 2009. After a postdoc at MIT, he got a faculty position in Rice University in 2012. And now he's an associate professor of physics and astronomy in Rice. So his research interest is mostly in the small system collectivity. In fact, the famous paper from 2009, the JHAP paper, which started the whole business, was really due to his work. This is the proton-proton long-range correlation paper. But he also, at the CMS, he also pioneered the study of the CME related searches in the P-LED collisions. And most of his work is in the CMS experiment. He's actually also have a lot of leadership role in the CMS. But recently he joined the STAR experiment in 2017. I hope he will make more contributions in the US in the STAR experiment and also in the future data analysis. Because of his contribution, he got a lot of awards, including the Early Career Award from the Department of Energy. And so I think we're going to hear him to tell us the history and all these exciting results from the small system. Wei, it's your turn. Start.
Okay, so can you see the slides? Okay.
Yeah.
Okay, so thank you for the nice introduction, and thanks for the organizer for holding this seminar series during this special time. So when we can't meet each other, and thanks for inviting me to speak here. So I was asked to talk about flow in small systems. So I will review some of the lessons we have learned, and I will discuss some of the open issues and puzzles that we still don't understand, and then try to highlight some opportunities in the future. So, well, first of all, as you can see here, that the focal point of discussion is about the smallness of the size of the system. So the question is, what do we mean by small? Right? So how small is too small, and what is large, and how large is large? And how the size of system will impact the behavior of the system or the physics of system we're interested in, and what we can learn from the large versus small system. This is the questions we're trying to address in this talk. So this field is interested in the physics of QCD many-body systems. In particular, our key objectives is to look for the state of matter with deconfined quarks and gluons, and try to study its properties by going to extremely high temperature or very high baryon chemical potential. And also try to understand the nature of the QCD phase transition. Is there first order phase transition? Is there a critical endpoint, which is actually the main theme of this seminar series. Although I don't have too much to say on that in this talk. So I primarily focused on the high temperature size of the phase side. So what are the experimental approaches to study this physics? So we use, as we know, we use a lot of heavy ion collisions and to accelerate them to very high energy and to smash them head on. So here we can see the concept of large, meaning that the large ions, for example, lead ions, gold ions, where the original motivation is to try to create a relatively large volume so that multiple rescatterings, the partonic rescattering can happen so that the system can form into a thermalized medium. So that we can call it matter. As opposed to what we call small would be in high energy physics, we call it proton-proton, where there the size of systems are not of Fermi. So therefore, in general, we do not expect much chance for parton to be rescattered, to just collide and goes away. And therefore, we do not expect to see any QGP matter form there. And also the advantage to have a large system is that with a large volume, you will have a chance to see the interaction with the hard particles like the jet produced with medium, which is also unlikely to see in a small system. So here you can see what we mean by large and small. So indeed, over the past couple of decades, the heavy collisions at the RHIC and LHC has established the so-called standard model, standard paradigm of the heavy collisions, where the two nuclei come in, they collide, and shortly after maybe the collision forming over C, a covalent plasma is formed, and then rapidly expand, and later freeze out and hydrolyze and turn into particles that are detected by the experiment. So it's been found that the final state particles, the momentum distribution of final state particles, shows strong collective flow behavior, and which can be described by the nearly ideal hydrodynamics, starting with the system with a certain initial state, with certain energy entropy deposition in coordinates to base, which then turn into the momentum distribution and correlation in the final state, where we can observe so-called the radial flow boost from the spectrum of the particles, and also the anisotropy flow in the asymptotic distribution, all the Vn harmonics, which is closely connected to the initial geometry of the system. So there has been a lot of results and evidence about the hydrodynamic flow of the large systems, which I will just quickly review some of them. For example, we have the measure event by event V2 follows almost precisely of what you expect by the event by event geometry initially. And then we see the mass ordering of V2 with different particle species shows indicate the effect of the radial flow, common flow velocity, and also this higher order flow harmonics, this fine imprints of QGP can also be well captured by hydrodynamics. Although there's some tension, there's small discrepancy there, but there should be some details to be understood. But overall, so our conclusion is that in these large heavy-ion collisions, we have it can be described by nearly ideal hydrodynamics with very small shear viscosity e to the s, and therefore we call it nearly perfect fluid. And in particular, is the final state asymptotic anisotropy flows, the V2, V3 is directly connected or proportional to initial eccentricity to 3, almost linear form. So that's for the large system, and then as we said, we expect that we don't see the covalent, we don't have covalent plasma in small systems. So is that the case? There are different ways to see the effect of V2 or collective flow, and so here is my favorite way to look at the two-particle correlation function in delta eta and delta phi, where in the central collision, this is the ultra-central Lilac collision, you can clearly see the striking long-range structure in delta eta. Basically is extending over entire delta eta, indicating that this is a correlation involving pretty much all the particles. and then you see the azimuthal anisotropy in the other direction. And as you go to a small system, in extreme case, in the minimum bias proton-proton collisions, where the DNDA are different by the smaller by more than 2 order of magnitude, it seems like this structure goes away. If you see, it looks like a large delta eta. You see a cosine delta phi shape, which is consistent with what we expect from just momentum conservation. So flow appears to disappear in P. Well, however, then we should ask the question, then if this is the case, then what happens in the middle? So where or when or how does it turn off as you go from the large system to small system? Or is it really just, does the system size matters, or is the produced particle density? Or does it really disappear in PP? So maybe as you go to a smaller system, so the noise or the non-flow correlation becomes larger, that high flow signal, which is still there. So it's QGP, whatever it means, quote unquote, it's always a perfect, always show flow effect, no matter how small it is. It could be possible because if you think about the QCD is intrinsically non-perturbative theory at low energy scale. So therefore, it may not be surprising that if you make a many-body QCD system, it is naturally strongly coupled, as opposed to like a QED matter where at the fundamental level, the interaction is weak, but then it's surprising that we can make strongly correlated QED system. The all emergent effect come out of the QED system. So these are the questions we want to ask. And so in fact, already in the early days, RHIC in 2005, RHIC already studied small systems. That's a copper-copper collisions. Here you can see the B2, the function of the N part in copper-copper and gold. Where for the case of copper-copper, it's already the measurement go to very peripheral. The N part on the order of 20, even smaller, and these are already very small systems. And so we could have asked question, what happens if you go to even smaller system, go to PP? I guess the presumption at the time people have is that it's gonna probably go like this. Eventually we go to PP, the flow goes away, but it's not obvious if you look at the data. But of course, we also the precision of data ran out at some point. It's hard to tell really what was happening here. And even much earlier, many decades ago, people like the Fermi has talked about the statistical approach for the particle productions in proton-proton collisions. Landau also discussed the possibility of hydrodynamics in proton-proton collisions. And even in the 90s, there's a search, experimental search for quark-gluon plasma in proton antiproton collisions at Tevatron, where they have measured the average momentum for pion KM proton as a function of the event multiplicity, and where you can actually see that the increase, the way the three particle species maybe increase interact actually already shows some feature of the radial flow behavior. But of course, at the time, it wasn't conclusive. Okay, so now so let's ask the question, how small QGP fluid can be. So what happens when you make size smaller and smaller? So with the microscopic picture, so usually we say that hydrodynamics applies when the system size is much larger than the mean-free path, interaction mean-free paths. So like the particle undergo multiple scatterings, where the mean-free path is related to the density of the system or temperature, and also the coupling strength. We don't know the coupling strength is probably big in the QCD system. So if the coupling is on the order of unity, let's say, then what determine this criteria to whether hyperactive or not would be the combination of the system size and the temperature. This is much larger, greater than 1, then hydro probably applies. But of course, if the coupling is extremely strong, then that makes the mean free path much smaller, and then it also makes it easier for system to flow even the size is much smaller. So that's, for example, in the limit of the coupling go to very large in the ADI-CFT framework, you can also make a QGP fluid with much smaller size on the order of 1 over the temperature. So yeah, keeping this in mind, and then so how this relate to the experimental quantity that we can control, we can handle. So approximately, this is not exact, qualitative. So the system size temperature is roughly related to the multiplicity produced in the system, because the entropy density goes like the T to the cube, and the entropy density is related to the particle density of the system. So therefore, to study, to answer the questions of how small QGP can be, so we know what we can do experimentally to try to go to these extreme domains, extreme domains of the applicability of hydro by trying to lower the n-track, lower the multiplicity. You can also try to reduce the size of system by going to large AA system to proton-proton. You can also actually vary the collision energy. In principle, you can keep the system size fixed, and you can scan the energy. Well, of course, you have to stay above the crossover temperature so that the system is still in the partonic phase. And you can also study different probes, for example, hard probes, where in that case, the coupling will be different. The mean free path, you vary the mean free path, keep the system size fixed. That's also, you also try to go to test, at which point the hydro will break down. So this is approaches I'll take in the rest of my talk. Okay, so the first excitement about small system came around 2010 when we first observed unexpectedly that in proton-proton collision you can also see the flow-like behavior, flow-like long-range correlation. That is the so-called near-side ridge along the elongated structure along the eta. But this is not what's different from what I showed previously is that this is high multiplicity events produce more than 100 particles. So in this case, you have a small system size, but you try to push the number of particles, multiplicity to be very high to try to go in the regime that hydro may work. We do not see this structure in Monte Carlo PCM model, which indicates this is something new. So therefore, the immediate question that people can ask is whether we have some kind of QGP droplet that's formed in the proton-proton collisions at the length scale that smaller than Fermi. So can we have a geometric picture like this where proton-proton collisions with overlap region? Probably doesn't make sense, right? Because we cannot have the participant parton and spectator partons. The spectator parton, they will produce particles. They will not just fly down the beam line. So one can also argue that maybe this is something that indicates that there's no QGP anywhere. So we have been misled in the large system. And the effect is caused by something else. But by now we know that this is unlikely. So the proton-proton is a hint, but then a couple of years later, the LHC had the proton-nucleus collisions where the old experiment, for experiment immediately see the strong long-range correlation effect. So the effect is so strong that you can do a projection to the other 5 dimension and do the typical flow analysis that we often do in large system and extract V2, V3, be whatever. And also in PA collisions, it's slightly easier to think about geometry. So you can take the global model, think you have one proton accelerate, strike a few nucleus participants, and you can calculate eccentricity, even do some prediction using hydrodynamics. So this is probably easier to think about than proton collisions. Yeah, you can have a V2 and maybe E3. And then immediately the RHIC experiment went back to look at the Duran Gold data they took in 2008 and also observed the similar correlation in delta 5, although their eta acceptance is limited. Okay, so now the question is, what is the origin of these long-range correlation? What's the interpretation? Apparently, the one obvious candidate would be the hydrodynamic flow from the QDP fluid, where you start from initial geometry and followed by the final state interaction. So let's call that final state correlations. So where in that case, the V2 will be gradually built up as time goes on after the rescattering happens. It takes some time. However, at the same time, so in this small system, it has been proposed that there's another mechanism could maybe also give rise to the observed final state correlations, and which that's motivated by the so-called CGC model, where the correlation comes from the initial gluon wave function structure inside nucleon or nucleus. They form these domains of strong color electric field, where right after interaction, the particles will immediately be scattered in some preferred direction. So in that case, this initial state correlation that will be there at the very beginning. So these two mechanisms, in terms of time scale, should have difference. So if we can look at the timestamp of how this correlation is developed, we should be able to figure out which is which. But of course, we cannot. We can only measure the final state. So how do we differentiate between the two scenarios? So, okay, so first of all, in the large system, we are pretty much convinced that it's dominated by the final state correlations, like gold and lead collisions. Now, if you go to smaller system where the lifetime of system is shorter, so going to stop, then so what's going to happen is that you might be more sensitive to the initial state correlation, and also there might be a sort of pre-equilibrium stage where your hydrodynamics is not fully applicable yet, and this small system may also be sensitive to that. So your hydro description may not, your full hydro description may not work. So our approach is, so let's start from the place where we know our theory is well established, that's in the large system, and then examine all the signatures, all the observables down to the regime that we're not sure about the physical origin, to see so whether there's any evidence that hydrodynamic breaks down. Is there any evidence or is there a need to introduce additional physics like the initial state correlation? Of course, we can also start from initial state correlations and try to go the other way. However, the reality is that we do not yet identify a regime where the initial state correlations is unambiguously established. Okay, so before I walk through some of the experimental results, I want to make a quick comment on the event classification. So in the heavy collisions, we know that we often use centrality because that has a geometric meaning, but that's not the case in small systems. So in A collisions, when you vary the centrality, well, you kind of know the geometry, and you also vary the system size and vary the number of parts, the multiplicity at the same time that correlated. So whereas in a small system, the geometry do not really tell you much about system size. If you look at, like, let's say PP collisions, top 1%, 0.1%, the system size is more or less the same, right? So the size of the proton, but the multiplicity can fluctuate a lot. So therefore, event activity, it can be multiplicity or total energy, represents more the system size in the sense that which determines whether the hydro is applicable. So in my opinion, that's the better classifier to use. However, the drawback here is that it might be experiment dependent. So different experiments, they have different acceptance and so on. Therefore, that sometimes makes it harder for series to perform their calculation. So therefore, the only thing we could try to do is try to provide the full information, as much information as possible, like the fractional cross-section, average, multiplicity, and so on. So the series can repeat the calculation in the models. Yeah, pretty much you will see that the many observables are presented in terms of the multiplicity later. Okay, so first I'm going to show you the single particle distribution and look at some of the radial flow effect in small system. And here is some data for the spectrum of kaon, lambda, and cascade in different systems, Pp, Plet, and Lat, in different multiplicity range. So we can also look at different particle rapidity range. So I want to see how this spectral shape, in particular, we're interested in how the shape evolves with all these parameters, which can give us some idea about the properties of the system. For example, we can look at the average PT or average kinetic energy for different particles. Here, plotted as a function of event multiplicity for different systems, where you can clearly see at low multiplicity, the three particles, they are almost on top of each other. So this is known as empty scaling. Obviously, often seen in mice. And then as you increase multiplicity, and you can then see that there's the different species start to split, and they split in the mass-dependent way, where the heavier particle increase faster than lighter particle. So this is the indication that there seems to be some common velocity field that give a larger momentum push to the heavier particles. And you can also see the splitting appears to be larger for the smaller system than larger system if you're comparing a similar event multiplicity. You can see it's probably better by parameterize the sort of radial flow velocity using the Blasway fit. Here you can see the parameterized kinetic freeze-out temperature versus the radial flow velocity for Pp, Plet, and Lat. Only for the peripheral part of that 3 sets of points. From left to right, the multiplicity increased. What is very interesting, if you compare across 3 systems that produce similar multiplicity, let's say around 130 tracks, you can see that the radial flow is larger in Pp, smaller system, than in larger system like that. So some feature of the radial flow can also be reproduced by not only hydrodynamic model, but also color connection model, and also CGC model, where you have flask tubes that serve as the source of common flow velocity. But the observed system size seems to be in line with what you expect from the QGP picture, where you have smaller QGP that is more explosive, generate a stronger flow velocity. And you can also see these in the anisotropy flow V2, where the mass ordering in these 3 systems seems to be, the mass splitting seems to be larger in Pp than in Lat. So one important measurement that really provides a strong and more direct evidence that these correlations that we have observed involves all the particles is the collective effect, is through the so-called multi-particle cumulant measurement, where here you can see the V2 measured using different number of correlation of different number of particles, 4, 6, 8 as a function of event multiplicity and also 2 for 3 different systems. So there are 2 sets of points called V2, and one called V2 sub means that it has subtracted what's so-called non-flow correlation, but it's based on some assumption and estimate, which is model dependent. Therefore, so the V2 one should consider that these 2 set of points give us some idea about what's the uncertainty, which is of course very large as you go to very low interest. But if you look at the multi-particle correlations where the non-flow is negligible for high multiplicity region, you can clearly see that it's almost independent of how many particles you correlate. So clearly, we're seeing something that looks like a collective effect. So now, so whether this collective flow will eventually turn off as we go to very low multiplicity, and this is a question we want to ask, right? Originally, so does it turn off eventually as we're going down? So we run into the difficulty where the non-flow correlation is very become more and more significant. Even for the cumulant measurement, they have a big contribution, and so the sub-event cumulant approach has been invented and measured by the ATAS, which you can further suppress the non-flow, so that you can extend your cumulant measurement to even lower in track. For example, the V24 here, the blue points, this is 3 sub-event method where it goes to, this is P-lab, it goes to lower in track. It's run out of statistics at where, you know, we don't know whether it's keep going flat or start trending down. So hopefully, you know, in the future we can still improve this measurement with more data, maybe even go to higher order particle correlations. So I show you some data to discuss some qualitative features. So let's look at how the model calculation do in describing the data. So I show you the recent model calculation that we using the IP-Glassman initial condition, including the initial, including the so-called initial stage correlations from the CGC domains, then run through music and then URMD for the hydronic rescattering. You can see that so data are plotted as a function of n charge and compared to least data for many different systems like lead, xenon, P-lead, and PP for V2 and V3. If you wonder, you know, what this n track corresponds to the typical centrality, so I show you here, in lead, to this region, this region is very peripheral, like the 70% in lead. You can see that the calculation actually have a good description of lead, even down to this very peripheral region, something we didn't used to do in the past, but if you extend to this very peripheral region, it still works well. But it's not the case for PP and P-lead, so they generally miss. And so I should mention that the series, they tune their calculation with the lead data and then they apply it directly to small system. So there's no further tuning in small system. You can always tune again to match, you can eventually match small system, but that's not a good approach. So why we see discrepancy in small system? Maybe there could be modeling of the initial geometry. That needs to or maybe ETOS, that should be a different value, and maybe other parameters. You can always tune that. Or maybe the hydrodynamics really breaks down, meaning that the gradient is too large. You cannot just do first order gradient expansion. So maybe there are other sources of correlations like initial state correlation. But I should point out that from this model, the initial state correlation, they primarily show up at very low multiplicity. here, where the data has not been measured very well. But in high multiplicity region, they don't have a large contribution. So yes, let's walk through these three possibilities. The first, the role of the geometry. So whether we have any evidence that in small system, this Wien harmonics has some relation to the geometry. So the RHIC has done a scan of small system scan for P gold, D gold, and helium-3 gold, where the idea is to try to engineer the initial geometry of the system. For example, in the helium-3 gold, if you imagine that you engineer a system with large initial triangularity than the P gold and D gold. And the hydro calculations, it seems to here the sonic E by E Vishnu, it seems to describe the data reasonably well. But however, the more recently, if you compare to the IP glass model of music ULKMD, again, there's no tuning in the small system. You can see that they actually have a rather large discrepancy with the Phoenix data. So here, one main reason is about how you model the geometry of the proton. You can assume it's spherical, or you can assume they have substructure as hotspots, and you also have to fluctuate that, and that can make a difference. And of course, that's something we don't really know as a priori. So the question is, how do we model the proton eccentricity? And is there any way to, oops. Is there a way to measure that? That apparently limits our ability to make predictions in this small system. Well, let's say we don't know exactly what the correct eccentricity is, but we can still try to look at some universal features of the eccentricity of the small system and try to make some quantitative prediction that is less model dependent and can be compared to the data. So here, in this paper, so basically, if you have a small system, you don't have average geometry. So the eccentricity comes from just random position of your hotspot or source. You can show that the eccentricity distribution is universal. It just depends on how many sources you have. So that if you believe that the epsilon 2, 3 maps to B2 3 in a linear form, you can make some quantitative predictions. For example, for the higher order cumulant for B2, 4, 6, or 8, we said that they are approximately the same earlier, right? But if you can measure them very precisely, you'll find they are not exactly the same. There are some fine splittings that can be, that just depends on the number of sources that can be predicted by this model. And you can also expect that if you look at the ratio of V24 to V22, and that should be approximately the same as V34 to V32. But all these four quantities that are independent, that are observable, they should hold this scaling relation. So let's test that. So first of all, so let's look at the V2, the higher order cumulant ratios, 6 to 4, 8 to 6, versus 4 to 2 ratio. So the values of the ratios are predicted to be constrained along these lines. So these lines, you can see, is very close to 1, but it's not quite 1. There's a few percent difference. And the data points here, these blue points, the latest data at 8 TeV PLED, which almost lie on top of these curves. So it seems to be confirmed. And one step further, then how about the second prediction about the V2, V3 scaling? So there, the V3, 4 is something very hard to measure. It's a very small magnitude that requires a lot of data. And that has been measured. And where you can see here, these crosses at the V3, 4 to V3, 2 ratio in PLED is almost lying on top of the ratio of V2,4 to V2,2, exactly as we expected from the geometry. And that's not the case in LILAD, which is also expected because LILAD V2 has large contribution from the geometry, the average geometry. So from here, we can see that in this small system in PLAD, there's really the data can be well described by the geometry-driven physics. There's no need and also no room for additional physics. Of course, we can ask what happens to PP, but that has not been measured very well, and that's still something that will be investigated in the future. So related to that, come to the second point. So I found that these studies very interesting from Huichao Yu and their collaborators, where they try to run hydrodynamics to calculate the cumulants in PP collisions, where they found that you can the hydro fails to describe the PP data, not quantitatively, but qualitatively you got the wrong sign. And if you try to trace back the reason, seems to be that there is, if you look at event by event, epsilon 2 versus V2, there's a large nonlinear behavior. There's some nonlinear response. Okay, we know it's also there in large system, but at the same time, the response coefficient is also very small, like on the order of 0.1. This also this makes it harder. It makes it smearing in the V2 map from epsilon 2 to V2 much bigger, so that the V2 fluctuation does not follow the epsilon 2 fluctuation in PP anymore. So then you don't get what you expect from the eccentricity fluctuation. So this is a sign that hydrodynamics running PP may have some trouble. I haven't seen other model trying to do this yet. But meanwhile, the transport approach, the kinetic theory, you can shows that to get the magnitude of V2 in small systems in PP, you only need on the order of like a couple of scatterings. You'll be able to do that. So maybe that's a more effective approach to try to retain these linear relations. Instead of in hydro, you have to do continuous evolution, where maybe in some region you very very sharp hotspots and very large gradient. That may fail. So it will be very interesting to see, for example, in ANTT, what cumulant you get for PP. So maybe in the small PP or even PA, the more appropriate picture is a more dilute system with a few scatterings instead of a QRP droplet.
Wait, just a reminder, you have 15 minutes. 15
minutes, yes. Or I will then have a quick summary of the first part, where so the lessons we learned, we've clearly observed, we see a strong collective flow across all the systems, regardless whether PP, PA, or AA, with sufficiently high vorticities. We also have strong evidence that so these correlations are driven by initial geometry, at least for PA and AA collisions, so the high precision measurement. We don't know yet in PP, so that's still required. We have plenty of open questions, at least here it's currently at the low multiplicity region. So how low the collectivity can extend to, and so in the PP collisions is still a big challenge. The model, the hydrodynamic model cannot describe the PP yet. Maybe some model can fit the V2 too, but the cumulant seems to be a big challenge. This calls the question whether hydro applicable to PP or not. Okay, yeah, so I pause for a few seconds if there's any question on this part before I move on later. Okay, if not, then I'm going to, so next I'm going to try to shift the discussion toward the hard growth. Again, the idea is try to push to the extreme domain to test whether paradigm still holds or not. So previously what we did, we tried to shrink the system by going from large system to smaller system. So now what we can do is in a small system, we can try to increase the mean free path of the probe by looking at the hard probes, the charm and bottom. So those those parts that produce they produce earlier, then potentially they're more sensitive to what happens in the early stage, and they also they are at a perturbative scale, meaning that their coupling is hopefully weaker and can probe more finer details of the system, more sensitive to the size of the system. So in a large A system, in light collision, what we found is that the charm flow is actually almost as strong as light flavor at RHIC, both at RHIC and LHC. As you can see here, if you compare to D0 to K-on, they are low PT. There's some shift, maybe due to the mass effect, but they're really very similar. So the charm, which suggests that the charm probably has very strongly coupled system. So now, what happens if you reduce the system size? What do you see? Start to see the finite mean free path effect. Now, this is measured in P-lab. We go from less to a smaller system. We shrink system size by reducing the multiplicity, where you can see, well, there are a lot of particles, fortunately, but maybe we can focus on the K0 shot, the open square versus D0, where we can see that the charm still has fairly strong flow, but maybe there's some indication that's smaller than K. But apparently the experimentalists still have work to do to try to improve the precision of this measurement, especially at low PT. To go one step further, this is for the charm. So how about the beauty? So the beauty is even heavier and presumably is less strongly coupled to the system. So now what happens if we compare the charm versus beauty hadron flow in a small system? This has also been measured, although with limited precision yet. Here you see the blue points. These are the D0 decay from the B hadrons, or called non-problem D0, where, for example, in the 2 to 5 GeV region, you can clearly see that there's a strong indication that the B flow seems to be a lot smaller than charm flow. Seems to be consistent with the picture that we have a medium which interact with these hard probes and shows a flavor or mass hierarchy. However, there's a calculation from the CGC which actually kind of describe the trend of data. There's also I'll explain the reason more details if you're interested later, but basically it looks like it's not the two interpretation ties again here. So we can next we can also look at the open charm versus the hidden charm, the JIP side. The JIP side, you need to have for JIP side to flow in the QGP, you can have two charm quarks. They both strongly interact, and then in the end, they have to be substantial JIP side come from recombination to make the large flow. Okay, so now here, let's if you compare the prom JIP side flow in the green versus prom D0, they're almost the same, and they are both not very far away from K0 shot. Okay, maybe not the case at low PT, but at least the JIPS and D0 flow, B2 seems to be very close. This is surprising because, well, first of all, if you look at the calculation, the model calculation, the immediate, you put the drip size in a small system medium, you can't get such a large drip size. This calculation here. And again, the initial state calculation, the CGC model, seems to get the right magnitude of the data. So does it indicate that we are seeing these initial state correlations? So I have to see, and it also predicts that the epsilon V2 is the same as drip size V2. So it's something we can test late, hopefully in a few years once we have enough data. So I will summarize this part. We use a table here where it shows you what has been measured and what still needs to be measured. So in general, there are still a lot of work to be done in the area of heavy flavor in small systems. There has been a lot of measurement done for the yield of the heavy fluid particles and some of the V2 measurement, but in general, this still needs to be improved with much better precision. So for example, the from D0 V2 in PP has been measured, but the error was really large. Very hard to come to any conclusion. And the other things like the epsilon V2 could be an important important measurement, and also the barons, the term barons is also important to have some idea whether you see the recombination, the enhancement through recombination or not. Okay, so what do we have in the future? The future at LHC, so this is the table that summarized the proposed programs at LHC in the next, say, 10 years, where we'll have run 3 and run 4. For the P-lab collisions, we still expect an order of let's say maybe 6 to 8 improvement in statistics, and there will be a lot of proton-proton collisions apparently. In addition, the other smaller ion program, oxygen, for example, oxygen has been also proposed, and it's very likely to happen during run 3, maybe in 2024. And besides, between run 3 and run 4, there will be a lot of important detector upgrades. Will really make a big difference in extracting information out of the data. So there's still a rich program ahead. And I should also mention that at RHIC, so next year, so it's very likely, hopefully, that we'll have the first oxygen run at 200 GeV. And this, you can see, has a strong synergy with the LHC. So you can compare these two small systems at different energy. So for the oxygen, the advantage is that it's a small system, but it can provide you a better control of the initial geometry, which you don't have in P-lab collisions. So yeah, stay tuned. There's a good chance that we'll see some oxygen data next year. So I'll spend the last few minutes, maybe 4 or 5 minutes, to talk about so where else we may be able to find the quantum plasma. So we have been talking about those hadronic collisions in proton nucleus and AA collisions. But how about we try to push to extreme domains. So can we actually do smaller than proton? The proton is already very small, size of one Fermi. But no, there are smaller in terms of size. There's a smaller system like E+ E- collisions, electron proton collisions, and so on. Where so people actually in recent years has look at those data and try to look at the correlations and search for the RHIC, search for the V2 in those systems. So for example, in E+, E-, this is in Hera and Zeus, and this is the ATAS measurement in the ultra-peripheral AA collisions, where you look at a photon colliding on an ion. You can also, in the P-lab collisions, you can look at photon colliding on a proton. So far, there's no RHIC has been seen. In particular, in those systems, it's very hard to reach to high multiplicity. They get to 30, maybe or so. And so in this gamma equation, so alpha has shown is the result for V2. This is not a range, right? So V2, actually there's a difference. They have extracted the finite V2 in these gamma equations. However, the interpretation is still unclear. So whether we are seeing real flow or this non-flow effect. What do we see in the Monte Carlo model? Take the gamma A gamma P Monte Carlo model. Do we get V2 or not? But this is something that could be interesting, for example, at the electron-ion collider, where we have electron-ion collider, the energy is not extremely high, but the advantage is that you have very high luminosity and you have a lot of beam time. So this physics should be part of the program at the electron-ion collider. So finally, just to want to discuss some new ideas that ultimately how small system you can go, right? In the QCD system, ultimately the smallest system will be a single parton. So can we make a QGP out of a single parton? Well, of course, you will say that that doesn't make sense. You are talking about many body system, many body QCD system. How would a single parton be, show a collective effect? Well, except that we know that single parton they cannot exist in the vacuum. So imagine you put a single parton in the vacuum. So it's not possible. But if you do, so it has an infinite amount of energy. So it will immediately excite the quark gluons out of the vacuum, and then generate particles. That could look like an expansion process. And to mimic that process, we can look at the jet, the high energy jet produced in E+ minor in proton-proton collisions. At LHC, for example, where what you do is exactly you kick a parton into the vacuum, and it will fragment. So the question is, so what happens in the process of fragmentation? So we don't really have a first principle theory to describe the process of the soft fragmentation of a parton in a vacuum. So it could be possible that as the parton enters the vacuum, it start to excite partons around it and show some expansion behavior that generate collective effects. So in which sense that this soft fragmentation process could be reminiscent of the QGP expansion. And so maybe this thermal feature observed in E+ minus collisions 2 decades ago is related to the expansion of the single parton QGP in the vacuum. So that's something still we still don't have a good understanding of. Maybe in the future, so this is a direction one could look at. So if you look at in PCL, this is the plot on the right. It's a PCL. You take PCL and look at the jets above 500 GeV, and you can look at how many particles fragment out of jets. You can get really large high multiplicity jets producing hundreds of particles. And so if we rotate the axis, so now if we treat the jet axis as the beam axis and redefine all the angles and the eta and phi angle, we can build a two-particle correlation function, and they actually look not very different from the beam axis. This is PCL, of course, we don't see the ridge and V2, but maybe we can look at this in the experimental data to see if there's anything interesting there. Okay, so now I will summarize very briefly, because I summarized already earlier. It has been very exciting past 10 years with small systems. We understood better, by studying small systems, we understood better the collectivity and where we do expect it in the large system. And we discovered collectivity at where it was not expected, and we're making rapid progress in understanding. And furthermore, I talk about the exciting opportunities ahead in the future to where else we can look for collectivities, and possibly can learn about more fundamental natures of QCD in those most extreme conditions. Okay, so that's all. Thank you.